Hello everyone, my name is Sivathanu Kumar and I'm here to present my 568 special project titled Capacitance Based Flow Rate Sensor. A few details of my submission. The title is a capacitance based flow rate sensor. The format is format 2, which is a recorded presentation, and this is a particular hardware for my that is applicable for my graduate research. My graduate research is actually to be able to non-obstructively determine the flow rate in implanted pumps, and the program I've used for this particular device is Arduino. So a little bit about my graduate research. I'm looking into baclofen pumps. Baclofen pumps are pumps that are implanted within the body that's filled with baclofen, and this is an anti-spasticity drug that is injected directly into the spinal cord via a catheter. So currently, there's no easy method of knowing whether the drug reaches the intended location without a lot of interrogation with an external device as such, or other methods that require intervention. There's no continuous monitoring method right now. And there's also no way of immediately finding if there's a fault in the catheter or not. And coincidentally, there's also no way of predicting a fault in the catheter if a catheter is going to fail. And these catheters usually stay in the body for 5 to 7 years, and they need to be monitored at a constant rate because they have a 5% chance of failing that cumulatively accumulates every year. And if there is a suspected failure, there's a very long workup time for it. It's almost 3 to 5 weeks and costs a lot of money. So shortening that time period and that cost would be one of the best things that my device can accomplish. So there are possible solutions, two possible solutions in fact. First one is a continuous monitoring flow rate device that is implanted within the body, and then this device will be able to monitor the flow rate and relay it to the patient or caregiver and develop a historical database of whether the device is working properly or not. So the patient can just open their smartphone and see whether there is if the catheter is working properly or if the device is working properly, and if it's working properly then they have a peace of mind as such. So that's what I have implemented over here for this particular project. Another method is non-invasive imaging techniques. This won't be a continuous monitoring method. This will be more of a low-cost imaging method that will be able to determine flow through the catheter based on expansion of the tube whenever the liquid passes through it. But for now, I've implemented the continuous flow rate monitoring device that's based on capacitance. So this device I've named it Bacloflow because it's implemented for a baclofen pump. This is the second prototype, so it's version 2.0. It's a capacitor-based flow rate sensor, and the capacitor is made out of two copper plates that is masked with aluminum tape, and the entire device is shielded by again aluminum tape so that the capacitance stays stable. Because as you'll see in the further when I'm demonstrating it, there's a lot of stability issues with the capacitance. It really is affected by environmental changes and conditions as such. So there is a housing present that houses both these capacitive plates, and there's a hole for the catheter to pass through it, and that is how the capacitance is measured. So whenever there's a fluid that flows through the catheter, the dielectric between these two capacitors changes slightly, and this small change is then quantified to be a change in the flow rate, and that is measured. So here is the schematic of the device. So we have the Arduino, we have an OLED display, four pins from the serial SDA and the serial clock. We have the parallel copper plates which are connected to two analog pins, A0 and A1. A0 is the charging pin and A1 is the discharging pin. So one plate charges and the other plate basically is known for discharging and observe the voltage reading. This is a really simple representation of what I was trying to go for, because right now the device is based on the internal resistances and the parasitic capacitance of the pins. Previously, it was a little bit more complicated with a few more additional resistors and capacitors attached, but right now it's just the charge and discharge pin and the parasitic capacitance and the internal resistances. And we also have the DC powered motor which is used to pump the liquid through the catheter that goes through the entire device. So yeah, for the principle, we have the Arduino pin, and Arduino pin is not perfect, so it has a, you can consider it to have a parasitic capacitance that's grounded, and you can also have a internal pull-up resistor, as all pins on the Arduino have, that's connected to 5 volts. And the parallel plate capacitor, as seen in the schematic shown below, we have the A0, which is a charge that goes to the parallel plate capacitor, and then the other terminal of the parallel plate capacitor goes to the A1 pin, that's the discharge point, and that passes through the parasitic capacitance. So the effective capacitance would be, C effective would be C parasitic into Cu divided by C parasitic plus Cu. Cu is the unknown capacitance. The total charge Q would be C effective divided by VA naught. So VA naught is the charge at the charging pin, which is usually is the voltage at the charging pin, which is usually 5 volts because it's configured as high output. So with this, we'll be able to calculate the voltage across the parallel plate, the voltage obtained at VA1, which is equal to CP by CP plus CU into VA naught. And this voltage is constantly monitored because it updates, because the A0, the A naught charge is constant 5 volts. So based on the catheter, whenever there's a flow through the catheter, the parallel plate capacitor would change its capacitance, so Cu would change slightly. And since VCU is being monitored constantly, we'll be able to monitor the change in capacitance through Cu as well. So here we have the device video 1. So there are 3 states in which the device functions right now. The first state is to detect whether the catheter is present in the device or not. So this is when there is no catheter present in the device, so it boots up and it displays no catheter. Now we have state 2 and state 3 of the device. State 2 is when there is a catheter but there is no flow through the catheter, and state 3 is when there is a catheter and there's flow detected through the catheter. So the device basically shows whether there's flow or no flow. And I've recorded a 1 minute video showing this particular thing from the device. Hello and welcome to Bacloflow 2.0 demo, where we will be showing the working of Bacloflow, a flow rate sensor. We have a flow indicator and a measured capacitance in microfarad that is used to find out whether there is flow. We have an empty catheter passing through the device right now, and this catheter is connected to a motor that controls the flow. And these rubber tubings are also connected to a reservoir in which there is a liquid, and I am reversing the polarity right now of the motor so that the flow can start. The liquid starts to move into the motor from the reservoir, as you can see over here in the video. Yes, you can see it. And this liquid then goes through the tubing through the device as such. Initially there's no reaction from the device, but after 3 seconds you see that it registers as a flow. As you can see, there's a slight delay of 3.5 seconds for sensing the flow through the device. This can, however, be removed by optimizing certain parameters that will be dealt with when building the next prototype. Thank you for watching. So yes, there is a slight delay that's observed, and this delay, it's also akin to the it's also caused due to this delays which are introduced in the code as such, so that I could go through the data to understand exactly what is going on. And this was the serial plotter which I have, which is obtained from the device, and it shows the current normalized capacitance values. So this is when there is no fluid in the tubing and there's no flow, so it's between 76 and 74. And after this I changed the polarity of the motor, and you can see there's a sharp drop, and this sharp decline is observed when the flow is started and the water goes through the tube as such, goes to the sensor as such, and you can see that it goes below 70 microfarads. And that's how I've been able to form a threshold and say that okay, now there is flow is detected in this device as such. So possible improvements of the device. So the first one would be to improve the accuracy of the device and so that it works under various environments. As mentioned, the device right now is only able to detect flow because it's so sensitive to environmental changes. If you're able to isolate the entire device so that it's more it has a more stable response to the change in flow between it, then we'll be able to quantify changes and then be able to exactly determine the flow rate through it. And the flow rate for these baclofen pumps or implanted pumps in general is very low, so being able to detect such a low flow rate will also be slightly challenging, and therefore adapting the device in such a way that it will be able to even detect such low flows is going to be like a further possible improvement. Then also implementing Bluetooth connectivity, because in the end it is going to be an implanted device, if we do continue to go down this path. And if it's going to be an implanted device, there has to be some way of communication from the device to the outside. Currently they do have Bluetooth interrogators used for the implanted pump as such, so something really similar to that would be very useful for the device, and that's what we're planning to do. And of course minimizing the size and make it body compatible is also needed, so because it's going to be an implantable device. So finally, thank you for going through my entire presentation and staying till the end. If you have any you have any queries, please feel free to email them to me. And if you have any suggestions for improvement of the device, or even a completely different method of calculating flow rate, but it has to be non-obstructive. So if you have any other suggestions, then please feel free to contact me and tell me, because I'm open to all suggestions. So yeah, thank you.